never introduced. This is writing in Smith and Van. Most books follow similar. Switch off the That's okay then. Seems to be clear. You have to switch off all those lights. I don't know how to clean the dust. Slightly better. So, okay, is it visible at all? Somewhat. So, what we have here is a listed table C4, probably from Smith and Van. It says standard enthalpies and Gibbs energies of formation at 298.15. That's the first thing you have to notice, and that will be an important limitation. So everything is at, although it is not stated here, the standard means if the pressure is 1 bar, it will be stated somewhere at the bottom of the table. It's not stated where I am displaying it. So we see here joules per mole of the substance formed, where everything is in joules per mole. I'm writing it for those who cannot see clearly. First thing you can see is methane, ethane, propane, and so on, and miscellaneous organics. The value is delta HF and delta GF naught. So this is the enthalpy of formation, and the Gibbs free energy of formation. They are all per mole. So they both of them actually correspond to H and G in our notation. Because everything is per mole, and not total enthalpies, but per mole. This delta of formation, so we have already dealt with several deltas, and this is even more confusing. So the delta really means that they are finding some way, for example, methane is there, methane is formed. I can write this following formation equation for methane. This is what the formation means, and the delta H means it's the enthalpy change associated with this at 1 bar and 298.15. Right? So this would be enthalpy of CH4 minus enthalpy of C minus 2 times enthalpy of H2. This is what delta is supposed to represent. But effectively, they are taking, you see this convention that the enthalpy of formation of all the elements in the natural form, for hydrogen, the natural form in which it exists at conditions 298.1 is in the molecular form, not in the atomic form. You want to create hydrogen atoms, you have to do something special to create it. So all these gases are, for instance, and carbon, for instance, would be in the solid state, elemental state. So since these are taken to be zero, it is formed from the elements, are regarded as it's actually only a hypothetical reaction. So it is very confusing in my opinion. There is really nothing called formation here, and it's really confusing. This additional delta, because anyway you are treating the elemental enthalpies and elemental free energies also as zero. So we might as well call this as CH4 instead of introducing the artificial thing of delta of formation, as if there is another change here. Now that is one thing. The other thing is, you can see across some state, this state is given. Many of them have come with within brackets G, and some of them have within brackets L. Some might even have within brackets S. So what do you think the G and L mean? G is gas, that everybody understands. L is liquid. But what does it really mean? For instance, let's take now an example. I'll tell you an example, give you an example. So both are listed. Now here we see way down ethanol. We have ethanol here, C2H6OG, and some values are given. Ethanol, C2H6OL, and some values are given. So how can ethanol, the temperature is 298.15, pressure is 1 bar. Ethanol, what is ethanol at 298.15 and 1 bar? It's liquid or a gas? Liquid. So how can, what is the meaning of ethanol within bracket G? So you must have all, at least everyone who has had some degree in chemical engineering must have used these tables. Is there anyone here who has not used these tables at one time or the other? So you use these tables without ever probably wondering, or you have forgotten what the G and L mean. So each one of them corresponds to a standard state. So can you tell me which standard state is G and which standard state is L? This is the ideal gas. Actually, G here refers not to the actual state of the substance at the given temperature and pressure, which you can easily verify. For ethanol, it is not a gas at 298.15 and 1 bar, so it cannot really correspond to the actual state. It is actually the ideal gas. Ethanol in its ideal gas state at 298.15 and 1 bar. That there is no contradiction in that. That is certainly a valid hypothetical substance. The L, even though it's not stated here, I will show you where it is stated. The L really corresponds to the pure component. So effectively, to summarize all this, what you would have to take is that if something happens with G is not even considered the Gibbs theory, if something is with G, let us take ethanol itself, G, and then you have a value minus 235, 100 below the enthalpy of formation. So for all practical purposes, this is in joule per mole, so convert it to kilojoule per mole. What delta HF not 298.15 Kelvin effectively means, this is 2 minus 235 minus 235.1 kilojoule per mole. This is for ethanol, and this is basically can be interpreted as HIG of ethanol. So in our notation, forget about delta formation and all that, and not and all. This is merely HI. This is the static state 1 and 298.15 and 1 bar. That's what you have to take it. In the same way, delta G, whatever its value is, that's in the second last column, that is to be GIG at these temperatures and pressure, 298.15 and 1 bar. Now if something has L or S within bracket, that would correspond to the standard state 2. So for the same ethanol, L, if you see, the delta HF is given to be minus 277.69. This actually corresponds to actual enthalpy of ethanol. all these enthalpies and energy basically, so everything has some reference state. And the reference state probably is just the elemental state, and for all the cases they are taken easy of all elements in the natural state. Right? So you can just proceed without worrying about how they can all be taken to be zero. You can simply proceed with all the calculations with this matching of the values in the table with the quantities that we have introduced. Right? So we can see now, I'll show you where it is explained. It is explained, and this is something that you should pay attention to when you look at any table. Just in case it's explained here, you may not be able to read it, but anyway I'll read it for you. It says the standard property changes of formation are the changes occurring when one mole of the listed compound is formed from its elements, with each substance in its standard state at 298.15 Kelvin. Right? So this is only a hypothetical formation reaction, and I don't think it is really indicative of, for instance, I don't know how these values are, for instance, obtained for water. If you see 298.15 1 bar, everybody knows that water is a liquid, but still a G is listed. This clearly corresponds to the ideal gas quantities. How one would construct a reaction where water is in a standard state means what? It's in an ideal gas state at 298.15 1 bar is really absolutely ridiculous actually. So I don't think it refers to a practical experiment, but a hypothetical experiment where water, not even an experiment, a hypothetical state. It is an ideal gas state, right, of water. And standard states, it says gases, pure ideal gas at 1 bar and 298.15. So it comes right in the fine print. If you don't read it properly, you're bound to get confused. So it is stated very clearly. Liquids and solids, pure substance at 1 bar and 298.15 Kelvin. So you can infer from this, if something has within bracket L or within bracket X, then those are the true states of those substances at 298.15 and 1 bar. Right? So now, that is as much I want to say. There is some ideas for liquid solution also. We won't get into it. For instance, aqueous. That is a mixed standard state. So we won't get into that right now. You can take a look at it and see what it is. Right? So this is as much as the tables go. It's really very simple to interpret the tables. You should know anything which has G within brackets corresponds to standard state 1. Anything which has L or S corresponds to standard state 2. And all of them are the values of the enthalpy. We take them as absolute values of the enthalpies and the Gibbs free energy, specific Gibbs free energy at 1 bar and 298.15. Are there any questions? I'm going to switch off this. Any questions? Yes?
Every component has its hypothetical ideal.
Every component has its hypothetical ideal gas. That is something we have already discussed. That is a hypothetical case where the identity of the atoms and molecules are preserved, but the interaction between the water molecules are hypothetically turned off, let's say. So that is why you distinguish between water as an ideal gas. First of all, that establishes that there is nothing wrong with regarding water as an ideal gas at 298.15 and 1 bar, because it clearly means it doesn't correspond to the actual substance. It's a hypothetical substance. Right? So, the second thing is that water at 298.15 1 bar as an ideal gas is certainly different from ethanol. Not all ideal gases are the same. The identity of water and ethanol is very important. But all ideal gases have certain common properties, yes. Namely that the internal energy and enthalpy are functions of temperature alone, and the specific heat is also a function of temperature. Cp minus Cv is R. That is common to all ideal gases. But we can, in principle, certainly consider the ideal gas of any substance at any conditions of temperature and pressure. Something we have explained very clearly. It is very important for you to understand. Otherwise, you will get confused. When we introduce a departure function, that's exactly what I explained. H minus HIG T1 P1. I can write it for water at 298.15 and 1 bar. What does HIG at 298.15 and 1 bar mean? It has a very definite meaning, and the value can be assigned to it. Right? Any other questions? Okay, if not, we'll move on. Now you can clearly see one important limiting. So I said the right hand side of log Ka equal to minus 1 over RT. Switch on the lights. So we saw that log Ka is minus 1 over RT, and restricting ourselves to only pure component ideal, pure component standard state will be the ideal as pure component, actual pure component. This is now a function of T and PSS. So PSS now we make it explicit. So what to use the commonly available tables, PSS becomes 1 bar. But T can be anything. Reaction temperature can be anything. Need not be. But the values given in the table, right, are only at 298.1. So if the reaction that is given to you, anything involving methanol formation or ethanol formation happens at a different temperature, then we need to be able to calculate this quantity at that. So what is given or what can be calculated is this sum at 298.1. That's a big limitation. Right? So what do we do with the temperature? We cannot expect all reactions to be at 298.15. That depends on the particular reaction. So if we want to calculate it, what should we do? These are only the standard state. So I will do the derivation for the ideal gas standard state. Right? So the ideal gas standard, assuming all the components are in the ideal gas state. Now, development for other possible choices of standard state is similar. So if I have this, now the first step, there are two ways to do it. First is the relying upon. So basically, I can calculate log Ka at 298.15 for the given reaction. What do I do if I want to calculate the log Ka at some other temperature different from 298.15? Right? So first, an approximate step is that we have already seen 1 over RT squared sum over d equal to 1 to c Hj. This is also at the same temperature, obviously. Right? This is also at the temperature which we want. But however, if I assume this is now what we will call as delta H reaction standard state. We now specialize in standard state 1. So if delta H reaction standard state, which is actually a function of T, right? So let's say 298.15, I want at 500 Kelvin. So now I can calculate this at 298.15 by using the tables. So if I assume, make an assumption for lack of any other information, not always a very good, but it will give at least some approximate value. If I assume that the enthalpy change, standard enthalpy change of reaction does not vary that much or can be regarded as a constant over the range of temperature from 298.15 to whatever temperature I want, then clearly I can integrate this, right, and get the following, let's say much like the Clausius-Clapeyron equation. Much like the Clausius-Clapeyron equation, which will allow you to calculate the saturation pressure. If we assume the enthalpy of vaporization to be constant, this is also something like a Van-Hoff equation. So then I can write this as delta H reaction standard state at, of course, 298.1, because that's how I can calculate times 1 over E2 minus 1 over E1. So I go to the tables, calculate the enthalpy change in reaction at 298.15, assume it is constant, then it can be taken out of the integral. All I have integrated 1 over RT square. That's exactly 1 over T1 minus 1 over T2. So this will give you an approximate value. Now if I want a more accurate value, then I have to also consider the one is I can use this and integrate it and calculate. One way of doing it is use the Hoff equation, but then calculate the enthalpy change of reaction. What is it as a function of temperature? Okay? So to do that, what I will now assume standard state 1 for all species. Then it's easier to do. Otherwise, it is a bit more difficult. Anything what you need is a specific heat area. Okay? So that is readily available for ideal gases. So I can get it very easily done for this. So first thing I know, for any species J, it is standard state 1 means Ij. It's the ideal gas. It's a function only of temperature. So I can even disregard the dependence on pressure. Right? So I can clearly write this as plus integral D1 to D2. The D1 will be 298.15 for us. And so CPI that's all. This is now readily available in the form of tables in many Berry's handbook and many handbooks, the ideal gas specific heat. So now all I have to do is just calculate the standard enthalpy speed. So I multiply this by mu J, or maybe this should be G, and then sum over J equal to 1 to C. That's what we will be the so plus, so sum of the integral can also be written as integral of sum. So I can write this as in principle it's very easy to write down. So all I need is the, so this is the delta H reaction standard state 1 at D1. And so if for any other if we take standard state 2, let us say, then we would need the specific heat because that would correspond to the specific heat which will be a function of temperature as well as pressure. It's no longer the ideal gas. What we need is that pressure to be at 1 bar. So we would need the specific heat data at 1 bar. But if we can neglect the change, which might be readily available because 1 bar is close to 1 atmosphere, and atmospheric specific heats might be available. So this is delta H reaction standard state 1 at T2. So given the specific heat data, I can calculate the delta H reaction. This is now actually has to be expressed as a function of T because I want it at any other temperature. I want to integrate this. So this would be really log Ka of T2. Integral both 1 over RT squared will go in, right? And so if I want to, I can put this as a T prime square, T1 to T, any temperature that I want. So this would complete this and delta H reaction standard state T, which is will go in delta reaction standard state T1 if I want to make it at any temperature, then I will simply make prime the dummy variable and I can get this. Actually, it is being done. I probably it's easier to show this is very standard and YBC House has a big set of expressions. So let's just see if this is slightly clearer than. Very straightforward. Yeah, this is now clear. So, this is exactly what I have done. T naught, I have made it. T naught is 298.15. Right? So, now, since the form of the expression is very well known, AI plus BIE plus CAE plus BIE2 plus EAE power minus 2. Right? So, SS1 is ideal gas specific heat. So, first what I do is calculate this integral. So the AI term would give me delta A times T minus T naught. The BI term would give me delta B times T squared minus T naught squared by 2 and so on. Right? That's all. Because the A's and B's are independent of temperature. They are constant. What is delta A? It is simply mu I AI. Delta B is mu I BI and so on, which you can easily infer from the formula. Right? So now all this has to be taken and substituted, and another round of integration has to start. This time every term being divided by t squared. So clearly this one, delta reaction at T naught, is going to give rise to some term, and it's going to give rise to this. So all the constant terms in delta H reaction at T is going to give me 1 over T squared integral. If there is a constant term, which are the constant term? This is one constant term. Delta A times T naught minus is another constant. Minus delta B T naught squared by 2 is another constant term. And so on. All of those would give rise 1 over T minus 1 over T naught. When you integrate 1 over T squared, that's what would happen. You could clearly see. This is a very tedious procedure, but it can be very easily inferred. Right? By inspection, you can convince yourself. And then the delta A term, T over T squared, would give me 1 over T. So that gives logarithm of T over T naught. I don't know what happened to R. So R I have taken it to the other side. Right? R is here. Right? So then delta B has T squared. So when you divide by T, that is now going to give T. So that T squared by T squared will give me a constant. So that's just going to, when it integrated, gives delta B times T minus T naught. So I won't advise you to write it down. It's all there in the standard books, but you can easily do it. And I'm not going to expect you to remember this by any means. So this is what it is. And if you want, I can give a copy of this to all of you. But it is there in the standard textbooks, so you can easily get it. So it's a fairly tedious but straightforward procedure. All I have to do is to get the specific heat data. And I know, because all it requires is calculation of enthalpies at one temperature given at another temperature for the ideal gas, which we know very easily how to do it. Once you have it, it's a question of multiplying by this stoichiometric coefficient and summing it and then integrating again. Right? So that is what. So what it means is that with this expression for the standard state 1, I can calculate the Ka of any reaction, provided I know the Ka of the reaction at a particular temperature, which is going to be 298.15 for us. Now, how do I calculate that? That is calculated using, using this. So first I do 298.15, this is also 298.15. So I go to the tables and type calculate the Ka at one temperature 298.15. Then I have two options. One, calculate the enthalpy change at 298.15. Assume the temperature range or the temperature at which I require the Ka is not very different from 298.15. Maybe over 200 or 300 degree Kelvin. You can take it as approximately constant, and then use this simplified form, or you have to use the more involved tedious expression that I just showed. In principle, we can do it. So let's now take a couple of examples, very simple examples. So just point out certain features, and then we'll see how to set up the extent of reaction calculation. So what I'm going to give is a couple of examples. Let's take this one. So I'm going to focus only on standard state 1. So now, if you look at the values, I'm just going to write out the values. So the delta G reaction, standard state 1, so I'm not going to mention it again and again, at 298.15 is simply, I go to the tables and pick up the values. You won't find any value for hydrogen, and it has to be taken as 0. And you see an element in its natural state at 298.15, which you have to know, but if it is not given, probably it is taken to be 0. Right? So that is something you should know. So I can write this as 3BH2 dissolved at 1 bar. Pressure is 1. Standard state means pressure is 1 bar, so I don't really have to write it again and again. But effectively, it means 298.15 1 bar, which we are by convention taking it to be 0, plus GCO 298.15 Kelvin, minus everything here is from the table, same condition, minus GH2O. Here by H2 I have to choose the gas, what is listed against the G, and again same condition. So if we put all these values into there, I would get, this turns out to be minus 137.2, so there will be many minuses, and minus, so let me put this within brackets. This is also given to be minus 50.5, everything is in neojoule per mole. Point out that the units you have to be very careful. And this is, we just saw, minus 228.6 kilojoule per mole. Everything is in kilojoule per mole. If I put everything in, I'll get delta H reaction to be minus 141.9 kilojoule per mole. Now, Ka, you can see, is, if I want to calculate it, Ka is exponential of this. Log Ka is minus delta G by RT. So, sign is very important. For example, we make instead of, there's so many negatives here, negative and then off negatives. Okay? And so, minus 149, you can see how much big mistake you will make if you were to change the sign, because it's all going to be into the exponential. Right? So exponential of minus 1 over RT. So R, if I take it in joule per mole, and 219.15. Times all of this, so this would be minus 149, so this would become plus 141.9, of course raised to the power 3. So it's a huge number. Oh, I'm sorry, this is not correct. This is actually plus 141. This will have a negative. So you can clearly see this is minus 136. And this together add up to minus 278 or 279.1. And that is plus. So plus 279.1 minus 137 would give plus 141.9. So you can check the calculation with the table. If you don't have the table, you have to believe what I say. So when I put this, so this is minus, so it's a very huge number. 141.9, of course you have 300 times 8, but it is still a huge number and it gives a very low value for the KA. I hope this is correct. Now we calculate similarly the delta H reaction at 298.15. And of course 1 bar is assumed. We have to substitute the enthalpy values in that formula. What you are getting is 205.8 kilojoules per mole. It's very interesting to know. The reason why I am putting all this not to show you the addition and subtraction, but this is clearly what is characterized as an endothermic reaction. This is the definition given. But you have to understand, I haven't said anything about what are the conditions under which the actual reaction is taking place. This is only the standard state. For instance, let us take some reaction. This is probably anyway a gas-phase reaction. Some reaction will be liquid phase. And if you use the ideal gas standard state, it is perfectly valid. So you get what is called the standard state enthalpy change. And then you make a conclusion whether it's endothermic or exothermic based on that. Right? So you have to see the somewhat of a contradiction. But anyway, this is characterized as endothermic, but very clearly what this means is that if I substitute it here, then you will see that Ka of T2 will be greater than Ka of T1. Because we are making conclusion about Ka basically, not about actually what is going to happen. Because Ka also has within it certain elements of the standard state. So there is nothing unusual about it. But you have to be aware, if T2 is greater than T1, that is the endothermic, that's what we expect. That if the temperature increases, the equilibrium constant, the activity-based equilibrium constant will increase. Right? So then we get, then you calculate at 500, this is now, you will see, the 205.8 is kilojoule per mole. It's a very hugely endothermic, which is then going to have a dramatic effect on the value. Now if I use get an approximate estimate of Ka using this expression, because I don't have the time to go through and gather all the specific heat data, you will find that this is still low, but it is orders of magnitude higher. And if I go to Ka at 1000 Kelvin, this is going to be 2.7. So you can see over a range of 298 to 1000, it is a factor of about 3.3 times temperature. The factor by which the Ka has increased is almost by 10 to 25 times. This is the effect of the endothermicity of the reaction. I would call it this is standard endothermicity, you can say, right, of the reaction. Similar example can be given. For instance, I have this other example which is exothermic. Take this other example, CO plus 2H2, the methanol formation reaction. To calculate the enthalpy, standard enthalpy is at 298.15. It turns out to be minus 90.2 kilojoule per mole. It's slightly lower in absolute values than this, about half of this, but it's negative. So it is still a strongly exothermic reaction. This is 90 kilojoules, it will be 90,000 joules per mole, which is a highly exothermic reaction. Now, if you see that the Ka at 298.15 can be very easily calculated to be 2213.1.65 and the Ka corresponding at 500 Kelvin, just roughly less than 2 times that, turns out to be 9.2 times 10 power minus 3. So almost a 6 orders of magnitude lower now with the factor of 2 increase, not even a factor of 2, less than a factor of 2 increase in temperature. So you have to be aware of these features of the reactions. So from the calculation of the standard enthalpy change, which you can easily get at 298.15, you get an idea of exothermic. Of course, the actual enthalpy, even restricting onto the standard enthalpy, is going to change with temperature. But probably the guess is it's very unlikely that a reaction which is exothermic at some stage will become endothermic at a different temperature. It can happen vice versa. But probably the specific heat contribution is not going to be that much to make the reaction endothermic or exothermic, change the nature of endothermicity or exothermicity as a function of temperature. What we can get out of the table directly is the standard enthalpy change corresponding to one or the other of the standard states at 298.15. If you wanted another temperature, you have to use the specific data and calculate. Are there any questions at this point? So let's now get back to the ultimate objective is to calculate the equilibrium composite. This is all the input that would go into calculating the equilibrium composition of the mix. Right? If we want to look at the equilibrium composition, then all this is entirely dealing with the right hand side basically. Calculating Ka, it is on the left hand side, but you are getting Ka by using the right hand side. The information is of the right hand side. The standard free energy changes and the standard enthalpy changes that are required. What we want is finally to calculate the Ka. So this is first what we have to do. Given a reaction, a single reaction, if I want to calculate the equilibrium composition of the mixture, first and foremost I have to get Ka at the given temperature. So what you do, you go to the table. So for that, what is you need the, if I want it at one temperature, at the given temperature, I need the standard Gibbs free energy change. Forget about the enthalpy. First I need the standard Gibbs free energy change at that temperature. So I go to the tables and I see I can only calculate it at 298.15. If the reaction temperature is also 298.15, we can proceed. Otherwise, we have to calculate Ka at the required temperature using either the approximate formula or the more elaborate formula, which basically involves calculating the enthalpy change, standard enthalpy change, which also I can calculate at 298.15. But with the specific data, I can calculate it at any other temperature. So the integrated forms are available, so I go and calculate the log Ka of T. The simpler one or the more complicated one that I showed on the transparency. Right? So once I have got that, then we need to look into what the Ka is actually composed of. Right? So we saw yesterday that the Ka can be split into various other Ks, and what we want most importantly is the bring in the mole fraction. So we saw that first step, if I take for example standard state 1, it is not very important what standard state I choose. So I take that all substances are under standard, we consider variations later. Under the ideal gas standard state, if I take, then we saw that the AJ mix for any substance, any of the species, is actually Fj mix by the standard state. It's going to be 1 bar, and we leave it as it is now. So what then happens to Ka? So Ka will become equal to Kf divided by TSS raised to the power delta mu. We saw that. And Kf can be further squared K is what I am calculating. I have already calculated it. Now I am going to look at what is happening to the components of K. How to split it into components so that I can get the composition of the reaction mixture at equilibrium. So Kf can be written as K phi times Kp. Right? But that's not very great. That is in terms of partial pressures by PSS to one form. But further can be written as K phi times Kz P over PSS. So now what is given and what is to be calculated, right? So first thing you know, the pressure integrity will be given, temperature will be given, and then you have to find the composition of the reaction mixture, right? So, but what is important here, the discussion of this in terms of the phase rule is somewhat awkward, because the point here is the pressure is given, the standard state pressure is known. Now what is Kz? It is pi J equal to 1 to C Zj raised to the power mu J. Now none of that I know. Right? So there seems to be C, not C variables, but C minus 1 variables. But we saw that all the mole numbers at any given time, once the initial mole numbers are given, so that's going to be another input. But the inputs have to be, this is not just a thermodynamic, but something more of a calculation. dP and Ni naught have to be given. Even though it might appear that I am interested in the composition of the reaction mixture, given the temperature and pressure, we now see that the actual mole numbers have to be given. Right? So the initial mole numbers are given, then we saw that each one of the mole numbers at any time later can be written in this some form like this, in terms of the extent of reaction. So now I can require this at equilibrium, because what I want is the equilibrium extent, or we will use a more convenient measure, the equilibrium conversion of a particular reactant. So what we now see, since each one of the mole fractions Zj is simply Nj times N total. So if I can get Ni or Nj at equilibrium I want, right? So each one of the mole numbers of each of the species can be expressed in terms of a single variable, namely the extent of reaction. So there are not really as many variables as we think there might be, because we are making use of the fact that the stoichiometry determines how the number of moles are going to change. They are not going to change independently, right? So everything. So if Nj can be expressed in terms of epsilon, Zj can also be expressed in terms of epsilon for all the j's. So clearly here there is only one variable epsilon. Because all the mole fractions can be expressed in terms of one way. That's a one-way unknown. That is all we are going to find. So we have one equation and one unknown. So what about K phi? K phi is quite, we run out of time, so we have to take it up some more.